learn about this one-dimensional harmonic oscillator. So we know that the Hamiltonian contains this kinetic energy, okay, and then plus this potential energy, right? And now we have two parameters. So the problem is defined by two parameters, m and omega, right? But we also have a constant h bar. Okay, so this factor leads to the typical scales, and this is something very important in quantum mechanics. Okay, so without the quantum mechanics in classical world, actually everything can be any quantity, but in quantum mechanics, because of the existence of this h bar, okay, so that's very important. Because of this existence of h bar, so we can always define typical scales. So you're going to encounter a lot of cases, you know, of typical scales in physics. But here we have, of course, a typical length scale. That is h bar over m omega, right? And typical energy scale, that is h bar times omega. And typical momentum scale will be just m times h bar omega, right? That equals, of course, and also h bar over LC, right? So these are the first of all thing that we have learned about this harmonic oscillator, right? So this harmonic oscillator has typical length scales, okay, and typical energy scales, and a typical momentum scale. So now you can, in units of this one, so you actually have got a Hamiltonian that's dimensionless. So this is very symmetrical, right? So with the commutator between these two, not just equal to I, right? Because everything is dimensionless in this Hamiltonian, okay? So that's one thing. So we have learn about this harmonic oscillator, okay? Right, and we find the eigenstates. Okay. The eigenstates, this person m actually can be written as you know, a kind of constant times a polynomial, and then times this Gaussian function. Okay. Of course, you can also change this one to be in the physical coordinates. So that will be divided by this square root of the typical length scales, make the dimension to be correct. Right. So that's the same, okay? And this HMX, I call the Hermite polynomial. Okay, we will talk about a little bit more about this polynomials a little bit later, right? And this normalization factor actually equals to and times the square root of pi. Okay, and this one actually is for the Gaussian function. Okay, and the in front factor is for the polynomial. So the energy is also very intriguing. It's equally spaced. Okay. Right. And the important thing that the ground state E0 that equals to h bar omega over 2. And this one actually is not 0, right? Okay. The reason about this one is that we have vacuum fluctuations. We have so-called, you know, this x squared equals 1 over 2. Xp squared equals 1 over 2. Of course, for the ground state. Right. And these are all in the units. So that, and also we have for the station state and the symmetric state, we have this one. Okay. So this means the variance of this one, all of this one, right? Okay. So you can see that that means the Hamiltonian. Okay. And this one is basically it's just h bar omega okay, right? So this one will equals to h bar omega over 2, right? So you can see that the fluctuation leads to the ground state energy. Okay, that's non-zero. Right. So this is very different from the classical mechanics. Right. Okay, so that's basically what we have learned last time. Okay, and now we can look at a little bit more future of these states. Right. So remember the state. Right, so this one gives you the decay at x goes to infinity, right? So that's the bound state. And this one gives you oscillations. Okay. And for the ground state, okay. So this is the ground state. So there is no oscillation. The state is symmetric, like this one, right? So that's the ground state. The energy is h bar omega over 2, right? So this is precise 0. And then you have the first excited state. Okay, the energy is 3 h bar omega over 2. Okay, and now this one is it's going to be anti-symmetrical, right? So it decays and it passes to 0. It's asymmetrical like this one. Okay. And then another state. So the energy is going to be 5 h bar omega over 2. Okay. And then this will be symmetrical and has decays and the symmetric. So like this one, right? So this is precise 2. This is precise 1, right? Okay. You can have say the even higher state, 7 h bar omega over 2, right? And now again you can have anti-symmetrical things, okay? Okay, this is a PHYS 3, right? Of course, you can go to higher and higher. Okay, right. And this oscillation is determined by this equation for the Hermite polynomials. Okay. Just by a little bit of algebra, we know that this polynomial satisfies the equation. Okay. So the coefficients will satisfy. So if you write this Hmx equals to A0 plus A1x, plus A2x squared, and so on and so forth. So you can lead to iteration relations between those coefficients. That is AK plus 2 equals to 2K plus 1 minus the energy, dimensionless energy, 2 epsilon m, and divided by K plus 2 and K plus 1, right? And of course, to make this one to be physical, boundary condition. So you have PHYS here goes to 0 at x goes to plus minus infinity, right? So this require, the series must be terminating. Okay. So that means this 2 epsilon m must equal to a certain number. Okay. Okay. Right. So that's the energy discrete. Okay. So this will give us the energy quantization. Okay. And also we obtain the series derivation of this polynomial. Okay. And the few examples, the first few terms, okay, of this polynomial. So you have, I don't remember actually. You're not required to remember all of these things. This is a specific form of this Hermite polynomial, but just to have some sense. Okay. So we have the zeroth order term. That's very easy, just 1, right? Because we know that the quantity is a Gaussian function. And then the next term is just 2x, okay, and then the second order polynomial is 4x squared minus 2x, okay, and the third order is going to be 8x cubic minus 12x. So you can see that this one has 1 term, right, and this one has 2 terms, okay. And also you can have, if you look at the fourth order, we have 3 terms. So you can continue this simply just by by those applying those series, okay. 32 minus 160 x cubic, and then plus 120x, okay. Right, so this one has 3 terms. Of course, you can continue this, right? But there is a formula. There are actually quite a few formulas, okay. And so there are a few important things is about this. There's a derivation of this so there's a generative function of this polynomial. So that is okay. So this is a generative function. Okay, and it has a name called Rodriguez formula. Okay, so if you really want to the explicit form, okay, so you can write down this one as expansion, but it has only finite number of terms, right? So for the nth order, if you have order 2, for example, you got the power maximum is to 1, right? And then okay, so this is the explicit form of right. So this is an integer number. Okay. So depending on whether this n is odd number or even number, okay, it could be just n over 2 or n over 2 minus half. Okay. So that gives us the the explicit forms of this polynomials. Okay. Right. So that's the things about this Hermite polynomials. Okay. And there's also quite a useful relation between those polynomials. So there's a recursive relation between these polynomials. The one thing is that so if you times x on this polynomial, you know that this is important, right? This is related to the application of the position operator, okay? So then you're going to have a so just ignore this, okay? Okay, so this is something important, okay? So related to the operator of this one acting on wave function, right? So that means more or less you can say that percent m, if you apply this operator, so you're going to get 2 terms, right? So that's if you apply this x on this Hermite polynomial, so you can say that you can get hm plus 1 and hm minus 1. So that means it's likely that you got a state percent m plus 1 and percent m, right? So this is something that we're going to use quite a lot. So that means if you have a state right here, you stay right here. So this is percent m, and then you apply this x. This will only go to the state up and state down, okay, by one state only, okay. So this one will not be possible. And similarly, this one is not possible, okay. So this is percent m minus 1, this is percent m minus 2, and this is percent m plus 1, this is percent m plus 2, right? So this is not, so it's not possible. Okay. Right. And also you have another formula is what if you apply d over dx, and immediately you can see that this is related to the momentum operator, right? And that's even simpler, okay? Okay. But remember, if you apply this one, So actually you need to act on this, right? And also you need to have one term on this one. So on this one, that will give us x times of this wave function, right? So this is related to the momentum operator, okay? So that means if you have cosine m, okay, you apply this momentum operator, you will also got a m plus 1 and the cosine m minus 1, okay? Even though here you only have m minus 1, okay? But because the differential of this one, we have two terms. So it's acting not only on this, but also on this, on the Gaussian function, okay? So that means if you apply the momentum operator, it will also go like this one, right? But it's not possible, and this one is not possible, and this one is not possible, okay? So if you apply the momentum operator on the wave function, on the eigenstate of this harmonic oscillator, will go up by one state or go down by one state, but it can never go by two states, right? So that's the use of this recursion relation, okay? Right. So this is one feature that we're going to use, okay? And there's also a nice thing about that. If we do the Fourier transform, okay, so you should define a state like this one. Right. And very interesting. So this one will just equals to the same form, okay? So this is something that you needed to keep in mind. So that's one very beautiful feature of this eigenstates of harmonic oscillator, okay? Except for quite a trivial coefficients. Okay. There's a phase factor here, okay? And this phase factor is no wonder because x and p, and you know, so this is related to the fact that so if you write that this is p, that equals to in terms of x, that's something like this one, right? But if you write x in terms of p, that is actually minus I d over dp. Okay, so you have done this one. Remember in the exercise class, right? Okay. Okay, remember this. So this tells us that they're not exactly the same, you know, because there's a phase factor difference. Okay, but otherwise, essentially, okay, it has the same form as in real space. Okay, I will not proof right here. Okay, for the proof, read the lecture notes. Okay. All right. So this is something that's very beautiful about this harmonic oscillator. It comes from the fact that you know the Hamiltonian is symmetrical in terms of position and momentum, right? Okay. So these states, all of these states, and this form a complete also normal set. We also call this one basis. Okay. The reason that it's called basis is that any functions can be expanded like this one. So first of all, this actually contains two facts. One is that if you do the integration of two eigenstates, so this will give us a delta function. Okay, so that means if they are the same, it's normalized. If they are different, it's just orthogonal. Okay, so this means orthonormal. Okay. The second factor is that for any function, for any normalizable, so if the function is normalizable, we can always expand this one in terms of its eigenstates. Okay, and of course, the coefficients can be easily obtained by the orthonormal condition. Okay. Okay. Right. So you can just use the orthonormal condition to obtain this one. Okay. So this is something quite easy, right? Okay. So this is another feature about this this eigenstates. So one more thing, okay? So we are like to study the fluctuations of any eigenstates, okay? Or variance of x and p of percent m. Okay. Now, first of all, we know that the average must be 0. This one comes from the symmetry, right? Because you have percent m, right? So this is even or odd function. So this is even or odd function. So even times even is even. Odd times odd is also even. And this one is odd, right? So if we do the integration, this must be 0, right? And this one, remember, comes from the fact that the bound state. Okay. So if I have a bound state, the average of the momentum must be 0. Okay. So this is one thing, right? And then we need to calculate the, if we want to calculate variance, we need to calculate this. Right. But then we can use the recursive relations, okay? I leave this one as an exercise, but I just tell you the effects, okay? Because the effects are actually more important than this derivations, okay? So if you apply this one on the state m, actually you got a state m plus 1 and m minus 1, okay? And the coefficient will be, this will be m plus 1, this will be square root of n, and divided by square root of 2, okay? So that is the, the use of this recursive relations. And similarly, you can apply this percent m on this one. And now you can see that there must be I right here because momentum operator is 1 of I, right? And there's also percent m minus 1, percent m plus 1, okay? And the coefficients is the same, except that this minus I right here, okay? Right, so this is also very important, results of this, action this operation of position and momentum operator on the eigenstates. Okay, and then you can see that now you can see that as we said before. Okay, so if we apply this twice, this one equal to what? So you can guess. So you must have, if we do this once, you got n plus 1 and n minus 1, right? So if we go higher, and this will get n plus 2 and n minus 1, and divided by some coefficient, this must be 2, right? Okay, and then you can see there's a certain kind of coefficient. Okay, there's a certain kind of coefficient. Okay, but for us, what's important is this coefficient. This is 2n plus 1. Okay, so I'd like you to derive these coefficients. Okay, but you can see that basically, if you have the state like this one, okay, and you can see if you apply x, you go up or down. So this is x, this is x, and then you apply this one again. So you can have this one either go up, this is x again, right? Or this also go x, or this one can go back, or go to this one, right? By x, by x. So basically, you're gonna have m plus 2, m plus 1, and m minus 1, and m minus 2. So starting from this state, okay, you start from this state, you're going up, and then going up or going down, okay? Or you can going down, and then going up or going down. So you're left with this one, or this one, or this one, right? So the coefficient will be, this one is 2, m plus 1. This one is something, okay? This one is something. I'd like you to derive, okay? Right? And then you can find the, what we are interested in is something like this one. So we are about to calculate this one. Right? But you can say this one has 3 states, n plus 1. So you're going to get something times m plus 2, right? dx. And then you something plus m minus 2, right? dx. And of course, there's one term that's interesting for us. Okay, but you can see that because of the orthonormal condition, so this one must be 0, this one must be 0, and this one must be 1. So the result is simply just m plus half. Right. Of course, you can do the same thing for the momentum state. Just do the same thing for this momentum state. Okay. So the result is also something percent m plus 2 plus something n minus 2. Okay, and then there will be important term, that's 2m plus 1 over 2 percent m. Okay, right? For the same reason, okay, if you have the state, okay, and then you start from say this is m, okay, and then you go to this state, right, by applying p once, okay, so you apply p, and then you apply this one once more, okay, right, so you get a m plus 2 and m or m minus 2, okay, right, so this is percent m, this is percent m plus 2, this is percent m, this is percent m minus 2, okay, right, so that gives us again, so you have percent m and p squared and percent m dx, so that gives us m plus half. Okay. right? So with all of this one, okay? So with all of this one, you actually obtained well, you can see that the eigenstate, the ground state has the minimal, okay, right? Fluctuations, okay. So let me recap this one. So for percent m, okay, you have x equal to 0 and p equal to 0, okay. And you have x squared equals to m plus half, and p squared equals to m plus half. So that means the fluctuation or the variance is something like this one. Right. And this also means okay, for ground state, okay. So if you have a ground state, this one actually is minimal. So that's why it's a Gaussian state, okay. We know that if you have a Gaussian wave function and the variance, the combined uncertainty of position and momentum is always a minimum, okay? Right, which is h bar over 2, right? If you recover the units. So we have done this one by calculation using the recursive relation. But actually, if you have some physical sense, you can actually obtain this one immediately, okay? Right? Why? Remember the H Hamiltonian just equals to h bar omega over 2 x squared plus p squared, right? Okay, so if you do the exchange, okay, so this Hamiltonian is invariant. So that means we must have right. So that means the energy, okay, must equals to right. But remember this one equals to okay. So from this one you can also immediately obtain, okay. So this immediately equals to right. So you can use the recursive relation to prove this uncertainty of the position and momentum. But you can also use some physical argument and quickly obtain this fluctuation, okay? Right, so that is the very interesting thing about this fluctuations, okay? Right, so this is the summary. Okay, this is obtained by recursive relations. Okay, but actually, you can have a quick derivation by physics. Okay, right. Okay, so I think it's about time to take a break. Okay, so see if you have questions. Right, so let's consider another problem of this one-dimensional harmonic oscillator. That is the time evolution. You're going to find that this time evolution is also very interesting and beautiful. Okay. All right. First of all, if I have a general state at t equals 0, okay, that's a superposition of different eigenstate. And according to quantum mechanics, so this one will evolve, okay, with the phase factor time dependent attached to each eigenstate, right? So this will be minus I em times t over h bar. That is, of course, it's R right here, okay, omega t, right? Okay, so this is the evolution, okay? And from this one, because of the energy levels are equally spaced, okay? So you can see that we have a periodical motion, okay? With this t just equals to 2 pi divided by omega, okay? This can be seen that if you have the wave function at t, and then after this time, okay, so this will becomes let me like this way, m plus half and t omega t plus t, right? But remember, omega t times t just 2 pi, right? So that will give us the same factor, except for this global phase factors, right? So this is the same state, and this one is a global phase factor, right? So that means if we calculate any physical quantities, so for any physical quantities, that will just equals to, right? So this means the system is periodical. So this is a very nice property of harmonic oscillator, okay? So it's always periodical motion, okay? And in particular, we are interested in the, the change of the position operator. Okay. Right, so that's something we are particularly interested in. Okay. And we know that this one is good about this, right? So you can insert this one into this, okay? So that will equals to summation of m and m. So you have Cm complex conjugate plus m complex conjugate e to I. The complex conjugate of minus I is just I, right? And m plus half n omega t, okay? And then times x, and then times Cm and plus mx and e to minus I m plus half omega t, right? And do the integration. Okay. Right. So then we have the integration of all of this one, can be done just by consider this state and this operator, right? So this one can be written as a summation of m and m, Cm complex conjugate, and Cm. And these two will give us minus I m minus m times omega t, right? That's the phase factors. And then you have another term, xm and m. So this one has been, we say that it's given by this integration. Okay. So we call this one a name, okay? So this one actually determines the amplitude, okay? Okay. So we call this one the matrix element. Okay. Right. So it's just the overlap. So you apply this operator on the m state, and then look at the overlap with the n state. So that one, we have a name called this one matrix element. But later we're going to see why we call this one a matrix element, okay? Right. And of course, we have, if we use the recursive relation, okay? Once more, right? Remember this one. Okay, so if I have a state, it goes like this one and like this one. So this is applying this x, right? So with the matrix elements, so this is percent m. So this will be square root of m plus 1 percent m. And this one will be square root of m percent m minus 1, right? So that is the, how we apply this x operator, okay? So this means the matrix elements will just equals to this is divided by square root of 2. So if m equals to m plus 1, okay, or it will be m over square root of 2. Square root of m over 2, if m equals to m minus 1, okay? Otherwise, it will be just 0, right? Okay? So this one gives us the selection rule. Remember this xt. Okay, if we times the charge, this is just a dipole, right? Okay. So it oscillates. So if it can oscillate only between neighboring states, okay. So now this one. So if they are low neighboring, okay. So that means you cannot have oscillation between states like this if it is separated by right? There's no oscillation, no transition, right? Okay. So transition occurs between M and M with M equals to M plus or minus 1, right? So that's a selection rule, okay? So this is a stronger selection rule than the symmetry requirement, okay? It's stronger than the parity selection rule. So in the parity selection rule, we know that if the two states have the same parity, there will be no dipole transition. Okay. But if you have harmonic oscillator, okay, it's actually stronger than this parity, okay. So that requires the quantum number is changed only by 1, okay, not only between order and the even parity states, but also the change of the quantum number m has to be only 1, okay. So this is one thing that we have for this dipole transition. And actually, it's similar for the momentum. Okay. So if we look at the momentum, it also have a matrix element. So that will equal to again use the recursive relation. Okay, you can obtain this matrix element. Okay. So I leave this one as exercise for you. So using the recursion, okay. Right. Okay. So that is about the time evolution, okay. And actually, for the harmonic oscillator, it's also interesting to, if you write this explicitly, so you can see that xt equals to summation of mm cmm, sorry, comes to cm e to minus I m minus m omega t, right? And x m m. And this momentum can be also calculated. That's almost exactly the same, okay? Except that you only need to replace this one, the matrix elements, okay? So this xmm, pmm are just matrix elements. So this will be clearer a little bit later, okay? According to Heisenberg and the Born, okay? Right. And now let's look at the, the time derivative. So that is very simple. You just need to apply this one to this time-dependent operator, right? So that equals to mm cm cm, okay? And now you have a minus I m minus m omega t x mm, okay? And remember this one the xmm equals to a the square root of m over 2 if m equals to m plus 1, or m over 2 if m equals to m plus 1. Otherwise, just 0. So then this one is either plus 1 or minus 1, depending on this one is larger or bigger, right? So if you compare this to the momentum operator, so this is I m over 2 if m equals to m plus 1. And this will be minus I if m over 2 if m equals to m plus 1. Otherwise, it's 0, right? Okay. So we have this. So if this one m equals m plus or minus 1, right? Let me use different color, okay? Okay. So you can say if m is greater than m, so m equals to m plus 1, so this will be just minus I. And then that gives us this minus I right here, right? Or if n is m minus 1, so this will give us minus 1 times minus I. That will give us I, right? That's this one. So that means this one times this one is nothing but just PMM, right? So that means this one just equals to, that's very nice. Okay, so we obtain the result. And similarly, I leave this one as access again for you. Okay, so it's very just follow the same procedure. So this way equals to minus omega. So there's omega right here. Okay. So this is quite remarkable, right? It's a closed set of equations. So that means actually, if we know this, so that will give us just like in classical mechanics. Right. So that's one thing. So that means, okay, if you know the initial values of these expansion values, and then all the length times will be determined, okay? And secondly, it's the same form as the classical mechanics equations, right? So you can see that the harmonic offset actually are very close to a classical system, okay? Right, the motion is periodical, and this expectation values, you know, follow the same equations as those quantities of classical quantities in classical mechanics, right? So harmonic oscillator is very classical. Okay, but it must be one, but not. Okay, because so this are obtained by many copies of measurements. Okay, so if we just do one measurement of this position or the momentum, you can just got a random value, okay? But you have to repeat this for many, many times, and then do the average. You can get this exponential value, okay? So this is fundamentally different from the classical mechanics. In particular, so you have this one. So there's always fluctuation. Okay. Right. So even though this equation of motions looks very like classical quantities, but still the harmonic oscillator in quantum mechanics is not a harmonic oscillator in classical mechanics. Okay, because of this existence of fluctuation. Okay, because of you needed to do the quantum measurement to obtain those expectation values. Okay. So by the way, and this one is called iron first theorem for X and P of a harmonic oscillator. Okay, so this is a special case of iron first theorem. Okay. All right. Any questions at this point? Right, so this is pretty much what we have for harmonic oscillator. You can see that it's very beautiful. And if you really want, I can, so the motion of this one. It's actually a circle. So if you look at the X and the P, so starting from this point, it's going to goes along the circle, okay? Right, so this is xt pt, okay, at the time t. So it's moving along the circle, okay? So it's a circle in phase space. Right, so this is also the same as in classical mechanics, right? So you know that the orbital of a harmonic oscillator in the phase space actually is a circle, okay? If you choose the units correct. All right. Okay. So if there's no question, so let me move on to another topic. So this harmonic oscillator actually has a very nice solution using this algebraic method. This was first done by probably Heisenberg. Okay. Right. So we define, this is ladder operators. Okay. One is called A. So we call this one a lowering operator. So later you're going to understand why we call this one lowering. The square root of x plus IP. Okay. And you also correspondingly have a raising operator. We put a dagger right here to denote the difference. And later you're going to also understand what is this dag. Okay. So these are the, now let's see these matrix elements. So we know that if you have states, remember, let me use larger. Okay. So this is percent m. This is percent m plus 1. This is percent m minus 1, right? So the energy are equal. So they like for the ladder, okay? And now suppose you have a state, you apply this x. Okay. So this we have said that this will give us square root of m plus 1 over 2, right? Times this function. Or if it goes to another state, that's m, okay? over 2 takes the square root, okay? Right? You can also do this one for the momentum operator. So you do this momentum operator, and this one actually will give us, I think it's I times square root n over 2. And for this one, it's going to be minus I, so m plus 1, sorry, m over 2, right? So this is the effect of these operators. But now if you apply this for this one, if you do this times I right here, okay? So you also times I right here. Okay? And then this will be I times this one, right? This will be I times this one. Okay? So that means if x plus IP, and then the result will be this one plus this one, that equal to 0, right? And if you to this one, so this will give you just square root of 2 times m, right? So this means, so if you apply this A on this one, so that will, so if you apply this A, that will only go to this one. So it cannot go to the state above, right? Right, so A plus m will equals to, you know, square root of 2m times plus m minus 1 only. But you need to divide this one by square root of 2 because there's a square root of 2 in the definition. And similarly, you can have this one. Okay? Because if you times minus I, so that will cancel another term, right? Okay? Right, so this one, that's why it's called a lowering. Why this one is called a raising. Okay? Of course, here we have already used so we have used the knowledge, okay? XMM, PMM, right? But actually, we don't need this one. A more elegant way is that, okay? So we can actually obtain these relations directly by the algebra method, okay? Using the commutators. This one are called algebra. Don't worry about the name, okay? Right, so we write this one. So A defined as square root of x plus IP, and A, another operator, is defined as square root of 2, and then you have x minus IP. Or similarly, you can have this is just work back, right? Okay. Right, so they are equivalent. And the commutators, we know that this one is I, right? So now you can calculate this operator. Okay. So this one actually equals to, there's a square root of 2 times square root of 2, right? Okay. And you have x plus IP and x minus IP. Okay. I can see that based on this commutator will give you, this I, right, times minus I, that will give you 1. And this one and this one give you minus I, but then you times I. that would be another one, right? So, but x and x commute, p and p commute. So the result is finally just equals to 1. Okay? Right? So the commutator we're going to use is just A and A DAG equals to 1. Or in other words, we say that A times A DAG equals to A DAG A and plus 1. Okay. Okay. Right. And the Hamiltonian. So by a little bit algebra, the Hamiltonian. So in terms of x and p was 1/2 h bar omega and x squared plus p squared, right? Okay. And then in terms of A and A DAG, so what I need to do is to insert this into this one, so you can obtain that okay. Be careful of the order, okay? But remember this one, okay, we can use this to replace this one. So you got a h bar omega over 2. So that comes a factor of 1, right? And then plus h bar omega A DAG times A, okay? Right? So this is the Hamiltonian, okay? And then we can say that this Hamiltonian and this lowering operator has a commutator just equals to, remember, h bar omega over 2 plus h bar omega A DAG A and A. Okay, so that will equals to h bar omega A DAG A times A and then minus A DAG A, right? Okay, and remember this one, because using A times A DAG equals to A DAG A plus 1. So you use this one to replace this, okay? And then you have minus h bar omega A, okay? And similarly, okay? And this one can be written as equivalently, it can be written as h DAG A equals to okay, equals to A times h minus h bar omega, right? Or okay, so this gives us a very interesting result. Okay, and from this one you can see that suppose I have a state %m. So if is % is eigenstate, and we don't know what it is. We don't know what is energy, but we can write down this one as %m plus equals to em %m, right? And they can say that then this one is also eigenstate. Okay, let me show this. So what you need to do is to look at this. What's the result, right? Okay, so this one, of course, can be written as this. Okay, and then you use this commutator between the two. So it can be written as okay. But remember, this one is the eigenstate of Hamiltonian. So that equals to, so this A right here. Okay. Right. So then you combine the two terms. It's nothing but just EM minus H bar omega times A percent M. So that means this one is the same as this one. So this is just eigenvalue. So this is eigenstate. This is a new eigenstate, okay? And this is a new eigenvalue. Okay? So that means, so if you have a state, percent M right here, so you apply this operator, Lorentz operator, you got a new state. We call it a percent M minus 1. So this energy is EM. This is energy is EM minus 1. Okay. Let me. So this is EM, and this will be EM minus H bar omega, right? And then you can do this one again, right? So you got a percent M minus 1. The energy will be EM minus 2 H bar omega. So you can do this once more. Percent M minus 2. EM minus 3 H bar omega, right? And so this is M minus 2, this is M minus 3. Okay. So you can continue this way. That's very interesting. Okay. All right. But we can also do the same thing for A deck. Okay. So similarly, you're going to have H deck, A deck percent M, that equals to EM plus H bar omega. Just because the commutator is slightly different, right? There's a sign difference. Okay. So that means this is the new eigenstate. This is the new eigenenergy. Okay. So that means if I have a state percent M, so you can, this is energy EM, you can go up, get M plus 1 by applying this A deck. Okay. You can apply this one further and further, right? So you can get a state. So this energy is EM plus H bar omega. This is EM plus 2 H bar omega. And this is percent M plus 2. Okay. By applying this one, okay. But you can also apply this, Lorentz operator. You got a percent M minus 1, percent M minus 2, right? And the energy will be EM minus H bar omega, EM minus 2 H bar omega. Okay. Okay, so this one just go down by A, and then you can continue this. Okay. But you can also go down from here, right? From here, okay. This is also A. This is also A. Okay. And similarly, you can also go up from here. A deck and A deck. Okay. Right. You can continue this. Okay. Right. So this form the equally spaced energy ladder, right? Okay. So that's why we call this one ladder operators. Okay. Okay. However, this one, there will be a flow because the energy, remember, equal to this one. Okay. So this one is always positive. Okay. And we know that it's actually greater than this one, right? So that means there will be a lower bound. Then, so there will be a ground state. Because that's 0. And there's no state that has energy below that to that, okay? So what does this mean? Okay, but if you apply, so if I have a ground state, so if percent 0 is ground state, okay, with energy E0. But we know that this one is E0 minus h bar omega times percent 0, right? So this one has a lower energy. So that means this should be impossible, right? So this data is impossible. In quantum mechanics, it's impossible. That means the probability equal to 0. So that means this state must be 0. Okay. And if this is 0, you know that the Hamiltonian is A dag A plus 1/2 times h bar omega. And now we're acting this one on percent 0. So that will equals to 1/2 h bar omega percent 0 plus A dag times A acting on percent 0. But remember, this one equal to 0, right? Right, according to this one. So that means the result is just 1/2 h bar omega percent 0. Okay? So we obtain the energy right? And of course, so E0 equals to h bar omega over 2. And then E1 will be just 3 h bar omega over 2, right? And E2 will be just 5 h bar omega over 2, right? And so on and so forth. Because we can apply this A dag. This is percent 0, percent 1, percent 2, percent 3, percent 4, so on and so forth. And this energy is h bar omega over 2, 3 h bar omega over 2, 5 h bar omega over 2, 7 h bar omega over 2, and 9 h bar omega over 2, right? And so on and so forth. Right? So we found all eigen energies. Right? Em equals to m plus half times h bar omega. Okay? And remarkably, so if we go back to the derivation, because we have only using a A DAC equals to 1. Only. Okay. So this is a beautiful demonstration of the method using algebra. Okay. Right. Okay. And then you probably wonder, so we know that A DAC plus M will give us a state plus M minus 1. But in quantum mechanics, there is always a coefficient, right? Okay. And similarly, you have this A DAC acting plus N will give you maybe another constant, C prime times M plus 1. The question is, C equal to what? C prime equal to what? Okay, let me use M to denote, this one could depend on M, right? Okay. I will not prove it right here, okay? So without proof, it's now difficult later. But at this point, I don't want to involve too much of this algebra. But the result is that A act on this one will equals to square root of M plus M minus 1. And A DAC plus M will equals to square root of M plus 1 equals to plus M plus 1, okay? So that is something quite useful. And similarly, so you know that remember this X equals to square root of A plus A DAC, and P equals to I times root of 2A minus A DAC. And then you use this one, you can obtain that so X, acting on plus M will equals to plus root of square root of plus 2 over 2 plus M plus 1 and plus square root of M over 2 and plus M minus 1. Okay, and the momentum operator acting on this one will equals there's I right here, right? So there will be plus I square root of M plus 1 over 2 plus M plus 1 immediately, right? So there's a minus I, sorry, minus I. Okay. So you just use this, action of this low variant and Racine operator. Okay. So in other words, we say that this has a matrix element. That's something we have already obtained, right? Okay. Okay. So this is the matrix elements of this. So you know that the exact coefficients of this, right? So you can see that this one is consistent with what we have obtained using the direct method. Okay. And this actually gives us, if you want to get a matrix, okay. But since we have know that this XMM, PMM, right? So suppose, okay. So now the matrix of this X actually can be written as 0, square root of 1, square root of 1, 0, and 0, square root of 2, 0, square root of 2, 0, 0, 0, square root of 3, square root of 3, 0, 0, and 0. So you can continue this way. Okay. And the momentum operator matrix will be this is square root of 1 over square root of 2 right here. Okay, sorry. So 1 over square root of 2. Just use the matrix element. Again, this is 0, but now this is minus I square root of 1. This is plus I square root of 1. This is 0. This is 0, and all of this one will be 0. This is minus I square root of 2. 0, 0, and 0. Plus I square root of 2. 0, and the minus I square root of 3, and 0. Okay, 0. You can continue this. Okay. Right. And if you look at this A, actually, it's even simpler. It just these two matrices, you times I to P and then do the summation, right? Okay, so that will be divided by square root of 2. So that will be actually square root of 1, 0, 0, 0, and 0, 0, square root of 2, 0, 0. So it's not any more symmetrical. Okay. Okay. So this is the matrix of this operator. And this one will similarly have a matrix. And let me just write down. Okay, you can try to demonstrate. And then this will be minus, the square root of 1, 0, 0, 0, 0, and 0, square root of 2, 0, 0, 0, and square root of 3, 0. Okay. So you can continue this way. Okay. So these are the matrix formula for all of this one. Okay. And then you can also obtain the Hamiltonian. Okay. And the Hamiltonian actually is even more interesting. So you just look at the Hamiltonian. So this one can be written as remember A DAG times A plus half. Okay. You can calculate the matrix element of this one. Of course, then times H bar omega, right? So the result is okay, H bar omega over 2. This is 1, 3, 5, 7, 9. All the others will be 0. So it's diagonal. Okay. So actually, you can see that. So this way we can actually go to these matrices for these operators. Okay. Right. And another interesting that so if you look at this matrix, okay, for this one, this is diagonal. If you take the transpose and then take a complex conjugate, we call this one emission conjugate. So this one actually equals to itself. Okay, so that means this matrix is so-called emission. Okay, or we say that this H is emission. Okay, you can check. The same for the momentum operators. But for these racing operators, actually, they do not use this one. Instead, you actually have this one just equal to this one. Okay, so you can go back to check the matrix. You can see that right, this one just equals to. This one just equals to, you do the transpose, and then do the complex conjugate. Right. So that means it's the emission conjugate of this matrix. Okay. And similar, this one equals to the matrix, the conjugate of that matrix. So that's why we put a dagger right here. Okay. Okay. So that's y DAG on raising operator. Okay. Right. So that's so finally we have a better understanding of this operator. Okay. Right. So there are a lot of other interesting properties. Okay. And I encourage you to just try to play as much as you can on these operators and read the lecture notes. Okay. Get you more familiar with this. Okay. I think it's kind of late. Okay, so we can probably stop right here, or yeah. So to see if you have questions. But so I have not covered all the this algebra methods and the interpretation of this this net operators. Okay, so do some practice on this and try to get familiar with these operators. Okay, it's a lot of fun. Okay, so let me stop right here and see if you have questions.